So, this is again the start of a new lecture, and in this lecture we start a completely different topic now. So, the past module, I think about 5 lectures or so, we concentrated 5-6 lectures, we concentrated on magnetic ceramics. So, in that module we basically discussed the fundamentals of magnetism, what is the origin of magnetic moment, what are different kinds of magnetism, how do you differentiate between them, and what is the origin for those magnetic mechanisms. And then based on that we moved on to magnetic ceramics, which are essentially ferrites, cubic ferrites, hexagonal ferrites and garnets, and then we looked at some properties with reference to the applications. So in this module now we'll focus on some of the exotic or a special kind of electroceramics which are not dealt in detail, any kind of detail in most of the textbook except a few, and at undergraduate level or senior undergraduate level or early graduate level there are virtually very few books which mention. So in this module we'll dedicate about a lecture each to these materials, so that I introduce you to them and give you some references which you can go on read later on. So this is module number 7, which is based on a special or exotic electroceramics. Now the first category in this first category of materials that we will talk about in this module is essentially high temperature superconductivity. Superconducting ceramics. Now, an introduction to high temperature superconducting ceramics does not happen without an introduction to the superconductivity itself. So what we will do is that we will initially introduce superconductivity, talk about low temperature superconductors a bit, some of the fundamental principles behind superconductivity, and then we will move on into high temperature superconductivity a bit, and then we will look at some of the applications which are useful. Now the reference book which I would recommend you to read is Principles of Electronic Ceramics by L.L. Hench and J.K. West, and this is a Wiley publication. So you can read about superconductors in this book, and there are numerous papers in journals and reviews which can help you understand this principle a little bit more. And again, there are several books, other books which can take you through this journey to superconductivity. Now, superconductivity, as the name itself suggests, it's like superconducting, materials which are highly conducting. And what this essentially means is that these materials have zero resistance in the superconducting state. Now, the superconductivity is essentially has remained a very hot topic for more than 50 years or so, and this is essentially because this ability to have zero resistance is something which is unique, and this can allow us to develop variety of applications without losing any power because of resistance of the material. So this is something which is essentially a very nice concept, a very nice philosophy, scientific philosophy, but it's very hard, it's not easy. Materials which exhibit superconductivity are also very rare. They are not every material on the earth exhibits superconductivity. Now, as far as high temperature superconductivity is concerned, this became an intense topic of research after the discovery of superconductivity in materials like, so high temperature superconductivity, it was discovered in an oxide of barium, lanthanum, copper, oxygen by Bednorz and Muller, and this fueled in 1986 basically, not too old phenomena, and this discovery which happened to show a transition temperature of 40 Kelvin, which meant that below 40 Kelvin these materials were superconducting, that is they had zero electrical resistance, was a major boost to finding superconductivity in oxides. And followed by this, in 1987 the superconductivity was discovered in another oxide, which is yttrium barium copper oxide, and this showed a TC of about 90 K, and this was a major boost to superconducting research because this temperature is very high. This temperature is higher than liquid nitrogen temperature, and that allows you to operate your devices at liquid nitrogen temperature, which is a lot cheaper than liquid helium if you had a TC below 77 Kelvin. So so commercially this made a lot of sense to have this kind of material which have high TC. So so this sort of set the tone for high temperature superconducting ceramics research as well as development of applications. Now what we will do is that we will first discuss the general aspects of superconductivity. Which will include first generation superconductors, followed by some of the basic principles such as Meissner Effect, etc., and then we will look at some of the high TC materials. So we'll start with discussion on low temperature superconductivity, and this low temperature superconductivity discussion will essentially to give you background information. Now superconductivity was discovered in 1911 by a Dutch scientist H.K. Onnes, who was basically studying the properties of liquid mercury at liquid helium temperatures, and then he suddenly discovered that below liquid helium temperatures or around liquid helium temperatures this mercury was superconducting, and that was something which was a surprise to him. And what essentially it meant was that the resistance as a function of temperature suddenly dropped to 0 at a particular temperature, and this was called as TC, or transition temperature or critical temperature in the lingo of superconductivity. So this is critical temperature. So beyond this temperature, essentially the material remains superconducting, and essentially the behavior is it's not like this, but rather it's sort of if you take it above TC, it's sort of like this, and then of course it follows some sort of power law when you reach normal temperatures. So essentially what it means is that there is a drop of temperature below, there is a drop of resistance, electrical resistance of the material to 0 ohms below a particular temperature, which is called as TC, or a critical temperature. And these first generation superconductors were essentially these first generation superconductors were essentially metals or metallic alloys, and they are called as essentially low temperature or low TC superconductors. And what do you mean by low TC superconductors is essentially the TC is lower than 30 Kelvin. That was the definition of these low TC superconductors, and the materials which followed this were metals and metallic alloys, and even in this there was a distinction. Pure elements like pure elements such as your tin or aluminum, etc., or mercury, these all elemental pure elemental metals, these were called as type 1 superconductors, and while the alloys such as niobium nitride alloy, niobium titanium alloys, niobium germanium alloys, and variety of other alloys, they were called as type 2 superconductors. And what is type 1 and type 2, that will be clear to you in a while, but this was the definition of low temperature superconductivity in metallic systems before the advent of high temperature superconductivity. Now essentially this onset of superconductivity, when the superconductivity takes place, so you of course have a difference, you of course have a change in resistance. So if you plot resistance versus temperature, then of course you reach zero resistance. So this is 0, rho is equal to 0, followed by some sort of power law, and this power law could be anything depending upon the material or system. Typically it goes as rho is proportional to T to the power 3 or something like that. So this temperature would be called as Tc, and this line would be actually more like a straight line. So this is let me just draw it correctly. So this line would be more like a straight line before following some sort of power law, and this is your temperature dependence of resistance. But this is also accompanied by change in the physical properties. For example, one of these is specific heat. So if I now plot a specific heat, this is specific heat. Now scales are arbitrary, so except that resistance is 0 below Tc. The specific heat follows a linear relation. Cv is proportional to T at temperatures above Tc, but below temperature Tc it follows some sort of behavior which is exponential of minus alpha by T. So this alpha is some sort of a constant which depends upon material. And this abrupt change in, so you see that near the transition you have an abrupt change in the specific heat, and this abrupt change in the specific heat, if you are aware of discussion that we carried out during discussion on phase transition in ferroelectrics, such abrupt changes in physical properties like specific heat are signature of some type of phase transition. So essentially what you can say is that onset of superconductivity at T is equal to Tc, which is the critical temperature, is associated with some type of phase transition. Okay, so this is essentially physically what happens in superconductivity. Now superconductivity as a phenomena it's a purely quantum mechanical phenomena, and just like magnetism and modern and many other modern topics in physics, this is purely a quantum mechanical phenomena. It cannot be explained by classical mechanics, and for some time there was no theory to explain superconductivity. There were futile attempts made just by talking of some sort of superfluid or some sort of cooperative movement of electrons or etc., etc. But all these attempts which were made to explain superconductivity, they went in vain because they could not explain it very well. So what happened was, in 1957 BCS theory, which was coined after Bardeen, Cooper and Schiffer, three scientists. Bardeen was John Bardeen, and Cooper was Leon Cooper, and Robert Schiffer. These three scientists together, they discovered this theory in 1957, based on what is called as a formation of Cooper pairs in the superconducting materials, which gives rise to this kind of superconducting behavior, and for which these Bardeen, Cooper and Schrieffer all three got Nobel Prize of Physics in 1972. So this was a major discovery in explaining the theory of superconductivity, and this was essentially based on flow of some sort of superfluid, or you can say the current which flows in the superconducting state is nothing but due to flow of a superfluid consisting of what is called as Cooper pairs, or pair of electrons which essentially interact through the wire lattice interaction, and this was something which was very important to understand. And another thing which is noticed for many superconductors is that many superconductors have low resistivity, although it's a condition which is followed in many cases. It's not a necessary condition. So you can say low resistivity is followed, but not a mandatory condition. So it's not a constraint as such. Just like in ferroelectricity you have constraint like it has to be non-centrosymmetric. It's not a constraint for a superconducting state. Now we look at the formation of Cooper pairs in a while, how the BCS theory came into picture, but some other features of superconducting materials is they follow what is called as Meissner effect, and this Meissner effect is essentially an effect which distinguishes superconducting materials from the diamagnetic materials. Many times people confuse between these two effects, but they're not similar, they are very different. Meissner effect is essentially, it describes the response of superconducting material to magnetic field in the superconducting and non-superconducting states, or basically in the superconducting states, and this goes after two German scientists, Meissner and Oschenfeld, who discovered this in 1933. And what they discovered was that when a superconductor is placed in a magnetic field, beyond a certain field which is called as a critical field Hc, superconductivity does not exist, it vanishes. So even if you are below Tc, material when it is in superconducting state, it does not remain superconducting if you keep on applying the magnetic field beyond a certain extent. Now when the field is below Tc, then field does not penetrate the material, it penetrates only partially on the surface of the material, otherwise it's completely repelled, and this depth of penetration is very small. It's called as, it's about few 100 nanometer or maybe smaller than that, and it's called as London penetration depth. So what essentially it is, so when you have T greater than Tc, so if you take a superconducting piece of material, it's a normal metal. So normal metal, when you apply field to it, so this is normal. So normal metal means field penetrates. Completely. So we can write this is normal state, and so this is your material and this is your field H. Now when T is less than Tc, which means you are in superconducting state, then when you have this material and when you apply field, this field is like this, it bends around the sample like this. So you have massive flux lines on the surface but nothing penetrating inside. So the whole of the field that you apply gets repelled, and this repulsion is essentially explained in terms of what is called as a opposite magnetization. So which means material is doing something which is repelling the whole field. This is like conceptually similar to diamagnetism, but it's not diamagnetism, because this is a function of temperature. And so when you are above Tc, it's completely repelled. When you are below Tc, it's completely repelled. When you are above Tc, it's completely penetrated. So it's not diamagnetic effect. On the other hand, diamagnetic effect is essentially based on Lenz's law. When you apply field, you essentially create a current which gives rise to a magnetization which is opposing the applied field, and this is not which is happening here. So it's not a diamagnetic effect, rather it's called as a Meissner effect. The outcome is sort of similar because you get magnetization opposing the applied field, but the causes are different. So this is your field is repelled completely, and this thick skin around the material in which the penetration takes place, little bit thin layer. So there is some interaction which is taking place out on the outer surface. This is called as your London penetration depth, lambda, and it's of the order of 100 nanometer or maybe smaller. So so it's only up to this depth this effect is important. So that is why this kind of effect is very important in thin films, because thin films, when the dimensions of thin films are very small, they are less than 100 nanometer, then there are some strange things which happen with which may happen there. So whereas in bulk materials it's a fairly straightforward thing. So essentially the difference with diamagnetic material is diamagnetic materials follow Lenz's law, which means they have a current which gives rise to magnetization which opposes H, whereas superconducting materials have nothing to do with So essentially the effects are similar but causes are different. Both have negative susceptibility. So superconductors, you can say, have chi is equal to -1 below Tc, but it's positive when T is greater than Tc. So this is the essential difference, whereas for diamagnets this chi is not a function of temperature and it's always negative, and also there is a dependence on Lenz's law for a diamagnetic material. So this is a major difference between these two. So essentially, but what you can see that since in the superconducting state, when you apply a magnetic field, it completely repels a magnetic field, which means you can give rise to essentially very large surface magnetization which is opposing the magnetic field, and this can be used for a lot of good applications which we will see later, and this is very useful for variety of applications. So essentially essentially effect is because of just to summarize, diamagnetic effect is because of orbiting electrons which give rise to current which in turn gives rise to a magnetization opposing the magnetic field. In superconducting state it's not true, it's something else. Okay. So another concept which comes in the wake of this Meissner effect is called as critical field, and this critical field is essentially Hc, and so when you can say Hc, so when H is greater than Hc then in the, you can say, in the superconducting state, the material does not remain superconducting. So how essentially you see it as, so when you apply Let us say this is magnetic field, this is temperature. Okay. So, there is a correlation here. So, this is Hc and this is Tc. So, of course, at 0 field below Tc the material becomes superconducting. So, this region is superconducting regime. Anything above it becomes a normal. So, what you see is that the Tc of a material decreases as you increase the magnetic field. So, this is a correlation of Tc and Hc, and this Hc is given as H naught multiplied by 1 minus T divided by Tc square. So, this is the relation which relates Hc and Tc in the parabolic form, and so this is true for what we called as type 1 superconductor, this kind of behavior. In case of type 2 superconductor, there is a slight difference. Now, what essentially it is, in case of type 2, I will use different colors, in case, or I will use different plot, let us say. So, in case of type 2, so again magnetic field, temperature. Now, in case of type 2, you have similar effect here in the lower field side. So, you have Tc and then H, but what you have here is Hc1, and below Hc1 you have superconducting state. But beyond Hc1 the region is essentially, so this is normal state, and beyond these two you have normal plus superconducting, and this boundary between, so essentially this boundary between Hc1 and Hc2 below Tc is a region where normal and superconducting states coexist, and this is what is found in type 2 superconductors, and this is where the difference type 1 and type 2 came. Type 1 was mostly elemental metals and type 2 were mostly alloys, and this is essentially a very important, so basically what this critical field and Meissner effect do is that they essentially define a boundary between the when you draw a plot of magnetic field and temperature, they define a boundary between the normal and superconducting state and determine the field above which the material does not remain superconducting. So, this is a very important concept again, and the critical fields, for instance, for type 1 superconductor, so Hc for type 1 could be of the order of less than a Tesla or so, and for type 2 it could be, since they have this region where normal and superconducting phases can exist, the fields can be as high as 40 to 50 Tesla. So, this is the advantage with type 2 superconductors, that you can hold the superconductivity, at least some superconductivity, up to very high fields, and this is very important for application, from the application point of view. Now we come to what is called as theory of superconductivity. Now, theory of superconductivity, as we said, was proposed by BCS, Barin, Cooper and Schiffer, and this was essentially put forward in 1957 at University of Illinois, when these guys were working to explain the reasons, and this was essentially based on the formation of what is called as a Cooper pair, and this formation of Cooper pair and concept of Cooper pair was floated by Leon Cooper, who is one of the scientists who put forward this theory. So, this Cooper pair is nothing but a pair of electrons which moves together in the lattice, and this happens by interaction with the lattice. So, how you have here is, you have these lattice ions, and what you have here is, you have this pair of electrons So, you have this pair of electrons which interacts with the lattice, leads to some distortion in the lattice. You can see that these two ions are closer to each other. So, there is essentially there is an interaction of electrons and lattice which gives rise to formation of this pair of electrons. So, this is your Cooper pair, and this Cooper pair is supposed to be formed because of Coulombic attraction between electrons. You might wonder what is this Coulombic attraction between electrons. So what essentially it is, since you have a negative charge on the lattice on the electron, essentially this negative charge on the electron in the lattice leads to buildup of positive charges around it, and which in turn attracts another electron, and this sort of leads to formation of what is called as a Cooper pair. It's a very simplistic explanation that I am giving to you, but this is what it is in summary. And this Cooper pair is essentially stable only when the binding energy of this Cooper pair is smaller than the thermal energy, and this is why this superconductivity is a low temperature phenomena. So this since the binding energies are very small, as a result it is not seen at high temperatures. So essentially this Cooper pair moves through the lattice by distorting the lattice, and this sort of a demonstration of electron lattice interaction, which was also verified experimentally, where experiments were performed by taking different atomic masses, and Tc was noted down. And what the idea was, if I change the atomic mass, then if there is a lattice interaction, that Tc would change, and this is what was observed. So essentially the beauty of this whole phenomena is, the coupling of this electrical phenomena with respect to mechanical process such as distortion of the lattice. So this is what is essentially the theory of superconductivity, and the experimental validation which was done was essentially, you have temperature versus Tc versus root of 1 divided by root of A, and this was done for mercury, for instance, and mercury followed a sort of straight line. So this is, for instance, somewhere here you have mercury 203.4, here you have mercury Hg 202, and here you have Hg 200.7, and then 200.6, and so on and so forth, until you go to very high like Hg 198. And the transition temperature varies from, so this is your 4.12 Kelvin, and this goes to right up to like 4.18 Kelvin or so. So the transition temperature was varying when you change the atomic mass of mercury. And if you want to know about this, you can go to this reference in Physical Review, volume 78, page 477, 1950, and then another one, Physical Review again, and then volume 78, page 487, and again in 1950. So you can look at these two papers for experimental validation of the transition temperature in experimental validation of essentially interaction between the electrons and the lattice, supporting the idea of formation of Cooper pair through the lattice distortion. Okay. So now what we will do is that we have discussed this theory of superconductivity with a focus on fundamental principles like Meissner Effect and critical field. What we will do now is we will look at the high temperature superconductivity. And high temperature superconductivity, as I said in the beginning of the lecture, it was discovered in 1986 by George Bednorz and Karl Muller at IBM Zurich in 1986, when they discovered the superconductivity in this perovskite oxide, which was essentially lanthanum based. It was a cuprate layered oxide, so essentially lanthanum based cuprate, and they discovered this as around 35 Kelvin or 40 Kelvin, 35-40 Kelvin, and for which Bednorz and Muller they won Nobel Prize for Physics in 1987 in physics, and so this was just after a year of their discovery, one of the quickest Nobel Prize ever given. And this sort of created a lot of vibrations, a lot of flurry of research activities in superconductivity, especially high temperature superconductivity, because so far before this the superconductivity was limited to elemental metals and alloys. This was the first time when the superconductivity was observed in something not metallic, something which was oxide, and previously oxides were studied as a dielectrics and as a ferroelectrics, etc., and structures were fairly well studied, but this was the first time when something different was seen, and that too starting with a high temperature like 35 Kelvin. It's reasonably high as compared it was much higher as compared to at that time low temperature superconductivity. Now this was followed by discovery of another compound in 1987, which was yttrium barium copper oxide, and this was found in University of Alabama, where I think Paul Wu and his researchers, they made this discovery, and this has a TC of 92 Kelvin, and this was a landmark discovery, because this gave rise to a hope that much more higher temperature, transition temperature materials can be discovered, simply because this 92 Kelvin, as I said previously, is higher than liquid nitrogen temperature, and that makes operation of superconductors much more easier and much less troublesome. And Paul Wu and his co-workers also found, so we can write the name, they also found that this superconductivity in yttrium barium copper oxide is highly sensitive to the composition. So what they found was, so this is essentially the formula is YBA2 Cu3O7 minus X, and this X was very important, and what they found was the superconducting state occurs when X is about 0.15, and this is what shows the highest TC. However, when you make X greater than or equal to 0.6, superconductivity disappears. Okay, so this is the sort of composition beyond which superconductivity does not remain. Now, followed by these discoveries, flurry of activities that took place on understanding the physics of these materials, how the superconductivity takes place, etc. There have been many attempts which have been made to understand the physics of these materials. However, unfortunately, there is no consensus on the physics of operation of these materials, how the superconductivity occurs in these materials. They are typically type 2 superconductors, but the physics of these materials is not known. So you can say that typically high TC oxides, essentially most of these are oxides, are type 2 superconductors, but the theory of the physics of operation, or just like you have a BCS theory put forward to explain low temperature superconductivity, the superconductivity in these materials is not very well understood. There have been some theories which have been proposed, essentially again quantum mechanical theories, but they have not been successful in explaining it completely. So I'll leave that out at the moment, but following this discovery of lanthanum based cuprate material and then yttrium barium copper oxide, variety of other materials were studied. So for instance, essentially the major focus was on thallium based and mercury based compounds, which showed much higher TCs. So I'll show you some of the structures. So compound, its TC and structure, and what you will see is that most of these oxides which were discovered, they had this very simple perovskite based layered structure. So that made life of crystallographers much more easier to understand them. So you can have, so the first thing you can have is yttrium based. So yttrium based was of course YBA2 Cu3O7. Now I am not giving the non-stoichiometry here. So most of these oxides show superconductivity in some sort of non-stoichiometry, and this Tc highest achieved was 92 Kelvin, and this has an orthorhombic structure. And then you have another category of bismuth based materials, and these bismuth based materials, variety of materials, Bi2 Sr2 CuO6, which had a Tc of 20 Kelvin, and this was tetragonal in nature. Now you can build upon this. Now this is Bi2 Sr2 CuO6. If you tune the composition a little bit, then it gets much more bigger unit cell, but at the same time the Tc increases. So for instance, if you make Bi2 Sr2 CaCu2O8, so you can see that you have increased the layer of calcium oxide, and when you put calcium oxide in the unit cell and increase the number of copper atoms as well, then the Tc becomes 85 Kelvin, and this is called as bisco. And this again has a tetragonal structure, much more bigger unit cell. Another one, you can make some more alterations. Bi2 Sr2 Ca2 Cu3O, again you can say that you have increased CuO and CaO2, so you have increased another oxygen and another copper O10, and this gives rise to 110 Kelvin, and this is again tetragonal. So if you change the bisco composition, you can have the Tc as high as 110 Kelvin. So this is a very nice discovery. The problem with these materials is that they are not easy to fabricate, and that's why BCO remained still a very popular compound. And another category is thallium based compounds, and in thallium based you start with Tl2 Ba2 CuO6, the parent compound, and this parent compound shows a Tc of 84 Kelvin, and this is again tetragonal structured. You can add some more atoms to it. Again you do the same thing that you did in bisco. So this becomes Tl2 Ba2 Ca Cu2O8, and this has a Tc of 108 Kelvin, and then you have Tl2 Ba2 Ca2 Cu3O10, and this increases the Tc further to 125 Kelvin, again with a tetragonal structure. And finally, when you make Tl2 Ba2 Ca3 Cu4O12, then this increases the Tc to, this decreases the Tc now. Any further addition does not increase the Tc, and this remains at 122 Kelvin or so, roughly similar. Another category that you have is of mercury based. Again there you have Hg Ba2 CuO4. Again you can see that all of these are cuprates. They have copper layers in between. So there is something to do with the copper layers which is important. Barium copper oxide in these layers, barium oxide copper oxide layers in these layers, which make them superconducting. So there is something to do with that which has to be understood. Ba2 Ca Cu2O6, and then you have Hg Ba2 Ca2 Cu3O8, and these have Tc's of 94, 128 and 134 Kelvin, again all with tetragonal structure. So you can see that these cuprates which have layers of copper oxides, they have, if you tune the composition by putting in variety of atoms in the structure, you can change the Tc quite well. The problem with mercury and thallium based is that mercury and thallium are difficult to handle. They are poisonous, and they are not something, and many countries have banned their use or restricted the use. So as a result they didn't pick up too much, but still huge research was done on yttrium based cuprate oxides. I will show you the structure of yttrium based cuprate oxide which we went through in module 1, just to recap what is the structure like. So if we go through this now, yttrium barium copper oxide. So essentially the parent compound is YCU3O9, and here copper is in +3 state, and this contains perovskite units, where the perovskite units would be some BO6 ABO3 kind of units, and these ABO3 kind of units are sandwiched in the layered form. Now what you do in this material is you dope this material by replacing yttrium with barium. So this yttrium is replaced by barium. So this modifies the structure. So essentially what you have is as a result, now the difference here is yttrium is +3, barium is +2, and this leads to a reduction in order to maintain the stoichiometry, this leads to reduction of Cu +3 to +2, and which results in the reduction in the number of required oxygen atoms, and hence what it does is it creates a vacancies of oxygen in the structure. So you understand that you bring in one barium, you of course reduce the requirement of oxygen. Now in order to compensate completely, copper also reduces itself as a result, because you have one charge deficiency here and another charge deficiency is caused by this reduction Cu2 3 plus to 2 plus to remove one oxygen, and this causes so the moment you do that, Y3Cu3O9, it becomes YBA2Cu3O8, and what you have here is followed by YBA2Cu2 plus 2 plus Cu3 plus, only one now, O7 minus X. So the structure changes like this. So you have this Y3Cu3O9 followed by YBA2Cu3O8 and then Cu3 plus to 2 plus, formation of YBA2Cu2 2 plus Cu3O7. So structure remains similar, orthorhombic structure, but what you have here is, as a result of these substitutions and reduction in the oxidation state, what you have here is vacancies of oxygen, and these crosses are nothing but vacancies of oxygen, and this also leads to changes in the coordination of copper atoms. So what you have here is essentially 5-fold coordination of copper 3 plus atoms along these rows, and then within these and within the plane you have this 4-fold coordination of copper 2 plus atoms. So this gives rise to anisotropic behavior in terms of conductivity of these materials, and so this is one primer on the structure of these materials. Similar structure, similar kind of tuning can be done in other superconducting oxides to give rise to a variety of structures that we have seen. So essentially just like you have formed YBA2Cu3O7, you can start from Bi2SR2Cu06, and then you can keep on building using these copper layers, copper oxide layers, by replacing copper with by putting in calcium, increasing the number of copper, change the TC, and this can happen with bismuth, thallium and mercury based, all these three types of compounds. So this sort of gives you a sort of understanding of what happens in these superconducting oxides. Now the superconducting oxides, since the TCs are typically higher than 77 Kelvin, which is liquid nitrogen temperature, they have been thought of they are used in variety of applications, and these applications could be you know, like magnetically levitated trains. You can have MRI imaging, you can have superconducting tapes, so a variety of applications have been proposed and some of them are already under use, and this is essentially because of this fantastic nature of this material, that it has a TC below which it remains, it offers zero resistance, and also below TC it offers complete repulsion of magnetic field as long as the magnetic field is below TC, below HC. So this is what is a very good quality of this thing. Material can be used in a variety of forms. It has been studied in thin film form. Thin film forms can be made by a variety of techniques. You can use physical vapor deposition methods. So essentially what you do here is you take a oxide target which you either sputter or laser ablate on the substrates which are lying under, and as a result you can make thin films of YBCO for thin film applications. And if you want to make bulk forms, then in the bulk form, just by mixing the, so if you want to make YBCO, YBA2CO3O7, for this you take yttrium oxide, barium oxide or barium carbonate, and then copper oxide, Cu2O or CuO. Mix them together in stoichiometric quantities, and when you mix them together they form, they react with each other at high temperatures to form the desired phase under controlled atmosphere and temperature. So under controlled conditions you do that. Similarly, thin film form are made by physical vapor deposition process. You can make thick films as well, and these thick films are used in superconducting tapes. So for instance, one of the uses of these YBCO is in conducting tapes, and these conducting tapes, of course you cannot make a tape of a standalone ceramic because ceramic is brittle in nature. So as a result you have to put it on a substrate, and this substrate has to be ductile so that it can take this, it can sustain the weight, and it can keep the ceramic crack free. And these thick films are typically deposited on nickel tapes, and these nickel tapes, they have some adhesion layers in between, and the thick films are formed by processes such as liquid phase epitaxy. So essentially you melt the YBCO material and you draw the tape through the melt, and YBCO deposits on the nickel tape, and it solidifies and forms a thick coating on top of nickel tape. So this is another form in which YBCO can be used. I'll show you a couple of pictures of applications of these materials. So for instance, one of the applications of superconducting ceramics is this magnetically levitated trains, as they are called as maglevs. Now these maglevs is essentially, so you have this train which is running on the race track. Now this race track of course has essentially there is no friction because of this repulsion. So you have this race track which can have superconducting material, and this of course has to operate at low temperature, and then and you can have this train which can have magnets at its bottom, and you know that since the field is repulsed by a superconductor, so the race track can be, you can have either of these two things. Either the track can be magnetic and the train can be superconducting. But whatever it is, because you have repulsion of magnetic field, these trains float in this magnetic field without any friction, and they can run at very high speeds, 300-400 kilometers per hour easily. And there have been trials which have been done in countries like Japan, and they're running in China and Germany as well. It's not a very common phenomena. It's not a very common mode of operation or travel, but it's something which has been used in some countries, and there are trials which are being made in some other countries as well. Another useful application is your MRI imaging, and this you must be more familiar. MRI is essentially magnetic resonance imaging, and this is again with the essentially if you look at this image, what you can see is various body parts and tissues, etc., and here you can find out essentially the damage which has been done in the body through this imaging. So what you have here is essentially the superconductor. When you cool a superconductor below Tc, it repulses this magnetic field. So this magnetic field which is repulsed is applied to the body, and this essentially what happens is then the molecules which are fat molecules and the hydrogen atoms which are in the water borne things in the body, they are forced to pick up the energy from the magnetic field, and this sort of and these species, they release their energy at a certain frequency which can be detected and displayed in the form of an image by a computer. So what you see here is, you can see a variety of ligaments and bones, etc. So any kind of damage that happen in any tissues and bones in the body can be very precisely imaged in this technique. This is very essential technique for these applications, health applications. So essentially you have these two applications which are of course in use. Superconducting tapes are coming in picture. There are some laboratories in America which are trying to commercialize these, some companies as well. So essentially, and so you can have thick tapes, and another application is essentially superconducting wires. And these are essentially composites. So what you have is a metal sheath in which you flow a superconducting wire. So you have metal superconductor, you have a metal, and between them of course you have liquid nitrogen flowing, and this can give rise to composite wire. You have to put a metal because superconductor is oxide and brittle material, so as a result it cannot sustain its weight when you have long cables and carrying the electricity. So but what this will do is that this will minimize the electrical losses and make the electricity transmission much more efficient and save money in terms of power consumption. So this is what is basically a primer on superconducting materials with some emphasis on superconducting ceramics. I have given you the references. You can go through these books and journals and reviews. If you are interested, you can go and read them. Plenty of literature is available on superconducting materials. So I think you shouldn't have any problem in getting more up-to-date knowledge in this area. In the next module, what we will do is that we will take up another exotic class of materials, which is multiferroic and magnetoelectric materials, which are again being researched in recent years because of their some fantastic properties, and that will take up in the next module. So just to summarize what we learnt in this module, we started with low temperature superconductivity, which are nothing but essentially metals and metallic alloys, type 1 and type 2 superconductors, and then we followed with the effect Meissner effect, which essentially tells you about the dependence of magnetic field and critical temperature. And what it tells you is that below Tc, when you apply a magnetic field above a certain level, then the superconductivity ceases to exist. And then you have the theory of superconductivity, which is by Bardeen, Cooper and Schiffer, and which is based on the principle of formation of Cooper pair through the interaction with the lattice. And then we looked at high temperature superconductors, essentially oxides, which were discovered in 1986, not too long ago, but there are some promising compounds like yttrium barium copper oxide, and the fantastic feature of these materials is that they are layered materials, so you can keep building layers and layers by chemically modifying them and change the Tc, and which has been observed in variety of materials. And however, despite all the advances, yttrium barium copper oxide still remains a favorite choice, simply because it can be made easily, and it doesn't contain any toxic elements which otherwise are present in other materials, and it has a Tc which is higher than liquid nitrogen temperature. So we will stop here, and then in the next module we will look at multiferroic and magnetic materials. Thank you.